Good morning to everyone. I'm Iñigo Molina Fernández. I am professor at the Malaga University at the south of Spain, and I'm going to talk about high-performance photonic integrated sensors. The work has been done in my lab. It's the Photonics and Radio Frequency Research Lab at Malaga, but also we have some collaborations with National Research Council in Canada, with Santa Ana, also with Oton, Professor Oton. Also fabricated the chips we are fabricating them in Cornerstone, which is in Southampton in the UK. And also we have some contribution from a recent spin-off of the group, which is Bioherent. Okay. So let's see, how can I go? Okay. So just to let the audience know where Malaga is, okay. This is Pamplona, this is Malaga, it's a beautiful place. I am also from the north of Spain, must say, but I have been 30 years there, and believe me, it's a beautiful place to live, okay? So there is very good weather, good beaches, good tourism, but still I have enough strength to keep all these people working. Have a group of about 30 people, okay, there. And Malaga is growing, okay? So there's a very important news in the paper recently is that IMEC, which is the biggest research foundry in semiconductors in Europe, is putting the second research facility in Malaga. Okay, they're investing quite a lot of money there. And for me, that I am in the integrated photonics, that will be, for sure, it will be good, okay? And also, I must say that in 2021, we launched this company. All what I present here essentially is the background behind that company. It's a biosensing company. They are developing in vitro diagnostic tool based in photonic cartridges for allergy to antibiotics detection, okay? They were invested by a venture capital with about 4 million euros, okay? And that has given us a lot of, new possibilities. So this is the scope of the presentation. I will go through an introduction, then we will hear these three pieces. They're very theoretical stuff. What, as an electrical and electronic engineer, what you should do and what you shouldn't do if you want to detect, biomarkers in a photonic biosensor. And then I will introduce some new concepts we are working on, which is complex sensing and multimode biosensing, which are like improvements, okay, that we are working on to support also that company. Okay, let's go to the introduction, okay. Of course, photonic sensors, we have a beautiful talk from Jose Miguel before. There are, thousands of applications. And also not only thousands of applications, but also thousands of different technologies, okay? So the first thing is to say where I am working, okay? So this talk is mainly focused in biosensing. We are going to do things like the ones you showed before, which is a platform in which you want to detect some kind of biomarkers, okay? Usually these biomarkers are in aqueous media, and that's important for the design, okay? And we are using telecom wavelengths. Of course, there is a multidisciplinary work, microfluidics, photonic chemistry, biology, etc. But I only work in photonics, okay? Okay, we are using integrated photonics technology because the group is essentially, we are designers of photonic integrated circuits. We are quite good in that, okay? So we are using silicon photonics platform. That means that the things that we do, we can fabricate them in massive form, okay? We can escalate them at a very low cost because we are using foundry services that are the same that are used for the microprocessors, okay? And we are using a measurement principle, which is a Van der field, refractive index sensing, is that we are going to measure the refractive index change of a medium on top of a waveguide through the Van der field contribution. Okay, I won't go too much about this. There is a lot of interest in developing point-of-care devices, and these photonic integrated circuits can be one of the tools to go from analytical laboratories, big facilities, to point of care and to have small instruments to do service for that. It's very important to know that in this kind of applications, okay, the specificity, you are looking for a target, for example, for a biomolecule, so the specificity is given by the chemistry. Photonics has nothing to say with that. We are not working in a spectroscopy or whatever, so we are not going to get a single bit of information of what substance is on top of the waveguides, okay? So that must be done by the chemistry people, by doing this biorecognition stuff. So they are, they are functionalizing the surfaces to put the complementary thing you want to capture. And his role is that, it's very clear. And which is the role of photonics? Well, the role of photonics is sensitivity. Okay, photonics is an incredible, sensible tool. And in fact, we are using this kind of hardware here, okay, which is an interferometer. And you say interferometer are probably the most precise and more sensible instruments in the world. LIGO, as Professor Seguera said, they got a Nobel Prize for this. Okay, LIGO experiments are, probably the most accurate or sensitive experiments in the world. Okay, so we're using that LIGO type of technology inside the chip, millimeter-sized chip. Of course, we don't get such precision, but it's not bad. So this is the people that is working in this. Jonas was the one who founded Bioherent. Most of the work that you will see here is from there. Antonia also finished his work. She was working, I think, first time we went into complex sensing, which means sensing not only the refractive index, but also the losses, okay, simultaneously. And all these guys, Anna, Laura, Ayesa, are now working with us, and they are, developing multi-layer capability sensors, or they are going to other frequency ranges, for example, for visible, etc. Okay, so let's start with these three topics, which are like theoretical background. So we will be using this evanescent field sensing. We have a waveguide. This waveguide is very small, silicon nitride, in fact, 1 micron by 0.3 micron. We decorate that with chemistry, with some, for example, antibody. Okay, so the field, we launch the mode field there. If there is a substance on the top, which is flowing an aqueous solution with some kind of substance there, your blood, your serum, whatever, and if you find there the antigen, okay, then it reacts with the antibody, and then you flow the light through it. As light passes through it, the evanescent field there interacts with that substance there, and then you feel that the refractive index, effective refractive index of the mode changes, and you just analyze this change. So the first thing is you must do is to analyze which is the aspect of the evanescent field. So I did these very simple, numbers for the slab. That is silicon nitride. Well, in fact, if you have a slab and you see there is a evanescent tail there, this evanescent tail has always this aspect there. There is a depth. How do you say this? This is the depth. I don't remember the name in English now. Profundidad de penetración. Sorry. Penetration depth. Okay. So the expression is very simple. You cannot do many things with this. If you have, for example, here silicon nitride will have 2. So at most this can be 2. This is going to be 1.3 or something like that. There is no much to do with that. Okay. We are limited. Okay. In fact, this is the number for silicon nitride. This is the waveguide typically we are using for 300 nanometer thickness. We get a 1.65 more or less effective index. So the penetration depth is 240 nanometers. Nothing to be done. If you want to reduce that, you are going to be limited there. Okay. So you cannot go very lower. You can go higher. Putting more field in the top, but you cannot go on the other direction. So we define what we call the waveguide bulk sensitivity, which is like, for us, is like our benchmark. Okay, we want to get very good number in this sensibility. What is this sensibility? Okay, if you change the refractive index of the cover, suppose this is water, you put a little bit of, I don't know, salt or whatever, okay, then you're going to change the refractive index of the mode, and that is the one you are going to sense. So we define this waveguide bulk sensitivity as the variation of the effective index of the mode, that is the one you are going to sense, with respect to the refractive index of the cover. Okay, and if you do this number, you find out that you have, specifically for this slab, you find like 0.14 relative index units per relative index units. That means that when you change one, the refractive index here, it only changes 13%, okay? And it's very, very much related to this number, which is the amount of the power of the mode that goes on the cladding, okay? So essentially, this number here is the amount of the field that travels through the cover, which is the one that you're going to sense, okay? Okay, so what about if we, instead of having all the, all the bulk here, you just perturb or try to sense what happens in a layer there, and you do the same number. You say, I change a little bit the refractive index of this layer, which is going to be the change of the refractive index of the mode, which is the one I'm going to sense. And then you can do this number, and this number is very funny because this overlap integral there says you that essentially this sensitivity is going to be proportional to this area with respect to the total area. There is nothing very new there also. Okay, usually in bio stuff, we have the perturbed layer there because we put here the antibodies, for example, so the perturbed layer is there, and then you can ask, okay, how, if we increase this layer thickness, how does this sensitivity change? Of course, when this layer becomes infinite, you have the bulk sensitivity there, okay? So 100% of the sensitivity is in the layer, but if you reduce the layer thickness, okay, you reduce this thickness, then of course you get lower and lower sensitivity. And if you look there, you have 86% of the sensitivity is in the penetration depth. So in the 250 nanometers, you have 80% of the sensitivity that you have available in the bulk upper part, okay? That is going to be important for the last part of the presentation. Okay, another thing that is very, very important in this, okay, is losses. Where are the losses here, okay? So if you look at the losses count, you have losses because of roughness, you have losses because of losses in the medium, and you find out that the only number that matters here are the losses in the water. So all the mode losses are conditioned by the water losses. And the number is very easy. You take the alpha of the water, what is this one over here, okay, and you just multiply it essentially by the bulk sensitivity, this 13%. So the losses are like 40% of the losses of the water, because only 40% of the field goes through the water, okay? So you get this number here, okay, which is, well, this is the number of the water, this is the number for the waveguide. So if you look at that, you find out that you have losses of the waveguide of the order of 0.08 millimeters to the -1, which means that the attenuation length or the penetration depth in the other direction, okay, is about 12 millimeters, okay? And that is very important also, because look, there is a lot of people working in this that is aiming to take all the field they can outside to the water, so that they say, okay, I have more field in the water, I increase sensitivity. But if you increase sensitivity, you increase losses. And at the end, we are telecom engineers, and we know that, the important thing is about, signal to noise ratio. Okay? So we are going to find something interesting on this. Okay, so which is the sense in architecture? Okay, now we know that we change the refractive index of the bulk medium. This changes the effective index. How do you measure the effective index variation? Okay, you just make the light to interact during some length, and then you have a phase shift. And this phase shift depends on the refractive index, so you can define what we call the architecture sensitivity. How much radiance does the phase shift change when you change the effective index of the waveguide? And that is how we measure that, and this number is architectural sensitivity. It's only the electrical length of the structure. So if you want to have good sensitivity, just do the structure longer, okay? And then put many wavelengths there, and you will have, increasing number there. You can increase that as much as you can, okay? You can put there, in the chip, you can put maybe 10 centimeters of waveguide, okay? Getting a lot of amplification there. But be careful, because you are going to get more losses, okay? Okay, there is a lot of people working in resonant. I work in interferometric, and of course I work in balanced interferometric, okay? Believe me, I can discuss with you, but if you want to do biosensing, just go to this solution. don't go to this one. Okay, this one is the way to reduce the size because you make interaction light bigger, but you know recirculating the light there. Okay, but nothing more than that. Okay, and it has a lot of problems also. So if you want to do the things nice, simple, and you don't need small volumes of sample, that could be a choice. Okay, just go for this interferometer, and please balance interferometer works much better than the other one. So this is the kind of architecture we are doing. This is the one we proposed with Jonas' PhD. This is the one that is being used at the, let's say, with some advances at the company. So we have a laser, rotation, polarization control, etc. So this enters into the chip. This is a disposable chip, okay, silicon photonics chips. You enter through a coupler. You have here, you see a much thinner interferometer. You plot a beautiful plot of that. That was done in Canada by our colleagues. We developed part of this with people in Canada. Okay, so usually these are spirals arms. So, okay, so it's the reference arm, and this is the sensing arm. One has a window, the other one not. Okay, well, both of them can have windows. And then we go to this 2x3. I will try to explain this. We have like, instead of having only one single output, we have like 3 different outputs. We do some, you know, detection, low noise detection. We do some maths there, and we sense with that, okay? And the key point is that at the end, what we are going to do is to find this phase shift, okay, through these signals, and we define the total bulk sensitivity of the system, which is how much change in phase when you change one RIU of the cladding, okay? And you can separate that in the architectural, okay? This is the architectural sensitivity, only depends on the length of the sensor, and the waveguide sensitivity only depends on the transversal section of the waveguide, okay? So you put the numbers there. For this silicon nitride waveguide is similar to the one we are using, okay? So for a 10 millimeter sensor, we are using more or less that, 10 millimeters in that order, okay? You get this number, 4 to the 10 to the 4 radian by relative index unit. You can do also the wavelength, the waveguide sensitivity, 0.25, okay? So the total sensitivity of the system is 10 to the 4 radians by each relative index units. And of course, you must take into account that you are going to have these losses for the total account. Okay, so now, why are we using this very peculiar way of, you know, receiving that? And that is important also for, you know, I saw your presentation, we're working detecting phases, okay? Why we use this kind of approach to detect the phase there? Because at the end, we are detecting phases. And it comes from telecom. I have been working in telecom for many years. And you know, in telecom, we are now using, you know, modulations with phase. So we are good in detecting phases, okay? And we know how to do that. So, okay, in the classic interferometer, suppose you have a classic interferometer there, you have a balances interferometer, okay? And then you have there some medium that puts some phase shift, and then you're going to beat that with the reference signal. You're going to have some amplitude detection there, and this is the typical thing you will find. If the phase changes linearly with time, you will find this interferogram, okay? And that has several problems, of course, because you usually only see which is the amount of the interferogram. So if you change, for some reason, the amplitude here changes, because there is some absorption, you're going to lose that, and you don't know exactly the reference. And also, you don't know if you are here or you are here. You lose your sensitivity there. So it has a lot of problems, okay? But people in telecom already solved that by using this, okay? So we use this in integrated. That can be done. We did that for the first telecom receivers at 100 gigabit per second for, you know, a company in Germany. So we knew about that, okay? So we are not doing this in the company with 90 degrees hybrid, but with 120, but you can find out that they are quite similar. At the system level, they are in fact similar, okay? So if you have this, that is 90 degrees hybrid and 2 balanced outputs, what you find out, if you do the same trial, you change the phase, is that you get these 2 signals, okay? And you say, okay, there's nothing very different. No, but this is very different if you plot this in the complex plane. Okay, if you plot this in the complex plane and you put there, okay, and you put there, you know, the I and the Q signals, you see that this is going to be a rotating, in the complex plane. And from that, it's very easy to extract the phase with no ambiguity, and it's very easy to remove any variations on the amplitude. Okay, so it seems you don't gain too much, but if you put it in the complex plane and you apply what we know from telecom, wow, this is the way to do it. Okay, so we are doing this. This is, again, the same, the system analysis. So we have the laser, we have the sensing and the reference arms. We have here two signals. One is the reference. The reference is only depending on the power. And the other one is depending on the power, the losses, okay, and the phase signal we want to detect. And well, if you look here, you have two channels. If you look at it as a complex signal, a real and imaginary part, you have like a complex signal which has this aspect. Fixed modulus and varying angle, okay? And of course, to this complex signal, you are going to put here all the electronic noise that there is there. Well, electronic and shot noise can be added there, okay? And it's fixed. I mean, it's fixed when you have your electronics. Essentially, it's going to be limited by thermal stuff of the TIAs, okay? So that's the way we understand this is done. And this is like a view of what would you see if you have, just some sample, I don't know, for example, water there, and you are in a steady state. What would you see? And what you will see in the IQ is that you have an I signal, a Q signal, which are static. So you have a point there on the complex plane, and that point has a modulus. And this modulus is going to depend on the power and also on the losses, of course, okay? And then it's going to have a phase, okay? And there is going to be some noise added there. But it's steady, but you have noise. And the noise, in communications is like a circle there, IQ circle. And the amount of noise, the variance of noise, is depending on the electronics, etc. Okay, but it's fixed. Okay. If you look at the phase noise, which is the important one, because you are detecting phases, you are going to see that the phase noise is curious, but it is reduced with the power, and it is increased with the length. Okay, because the received power is lower. So phase noise is this phase variation, is not the gross. So this is typical from communications. So as much power you put, you reduce your phase noise. Okay, that's clear. Okay, now, for some reason, the refractive index in the cover changes because you inject something and you are in another state. So what happens is that that vector has moved, okay, with the noise. And that's the one thing you are detecting, okay? So what you detect is this. This is the bulk sensitivity multiplied by the change in the refractive index that changed the phase of the signal. Okay, so now you can see what the LOD means. The LOD means that you must separate this from this by 3 times, essentially. Okay, so this is the LOD as seen in the complex plane. It's a very interesting view. Okay, you can remove all the amplitude noise because you are only detecting phases. Okay, I can do, oh, yes, oh, incredible. Wow, so I will have to come another day. Okay, so, yeah. You have completely destroyed my concentration. Okay, so now just I will finalize shortly. Okay, if you look at the LOD, you find how do these changes with the interaction length. You find out that the LOD depends on length because as you increase length, you increase the sensitivity, but also as you increase length, you decrease the power, okay? So there is a trade-off, and this trade-off is put here, and if you do the derivative of this with respect to L, you find out that you cannot increase the LOD by increasing L. You have to choose an L which is the inverse of the attenuation, okay? And then you find which is the optimum length is there, is used the 1 over alpha, and then you get this minimum number, okay, which is beautiful, depends only on the power you put, the sensitivity of the waveguides, etc., etc. And by doing all these numbers very, very well and very clever, we finally went to a system, demonstrated, that theoretically has a LOD that is really maybe 10 to the minus 10th, so you can detect the 10th difficult number on the refractive index, okay? And we experimentally demonstrated the value which was a state-of-the-art, I don't know now, okay, that was this number over here, okay, which is really a very, very good number. And just to finish, okay, I will not go through the other slides, of course. These are the latest experiments in biohealant concerning this. Okay, these first ones were done with water with salt. They were reducing the concentration of the salt and see the phase change. So they find out this data. Theoretically, they should follow this path, but they found out this. That is that when you reduce too much the concentration, you start to see problems of ionization of the salt on the surface. Okay, so they moved to DMSO solutions, and with that, they were able to show this very nice experiment. And this number over here correlates with a number which is 3.4 for 10 to the minus 6, which is a real stuff measurement there, which is not bad. Okay, if you look at the signals for that experiment, you still see that this concentration, it was the last one, that is 10 to the minus 6, you have a lot of signal-to-noise ratio, and the problem now is not with signal-to-noise ratio, with baseline drift, which is another issue. Okay, so, and of course you are losing the best of the talk, but I'm sorry, because I really, I don't know why I took so much time. Okay, thank you.
Okay, so thank you, Iñigo, for your inspiring talk.
Sorry for the time.
No, no matter. Okay, so we have kind of 2 or 5 minutes to ask for the speaker. Yes, we have a question there.
Yes, the second, let's go for the last slide. Yes, for advertising. Okay.
Perfect. Let's go.
Thank you for the talk, very inspiring. Since you mentioned that the Mach-Zehnder scheme is much better than the ring, the Whispery Gallery modes-based ring, I was wondering which are the main drawbacks
of the ring. Okay,
in comparison with that the Mach-Zehnder does not have.
Okay, suppose. Okay. So let's go for the basic stuff. Let me see if I have here. Okay, so okay, suppose you have this. Okay, suppose this is a balances interferometer. So the length of this branch and this branch, electrical length are the same. Okay, the sensor. Optical sensors have a lot of sensitivity, but the problem with sensors is that you have to have a very big sensitivity to what you want to measure and no sensitivity to other things. So one of the things we are doing here is that we don't need to sweep the laser. We are using fixed laser. Okay, you cannot do that usually with rings. You must use a sweep. Okay, we're working with fixed stuff. Okay, because we are looking at the complex plane and looking at the same frequency, which is that's one aspect. We don't need complex interrelation. This is fixed laser. But even better, suppose that this is perfectly balanced, okay, and you have their medium, steady medium, okay, and you change the laser, and you sweep the laser. Suppose this is not fixed, but you sweep it. What are you going to see there? Are you going to see any movement? No, it is balanced. Okay, if you change the frequency, you're going to change the angle, the phase shift of this and of this at the same amount. So this is going to be insensible to movements in the laser. So this is going to be insensible to laser phase noise. So you can put a very cheap laser source, even a broadband laser source if you do the thing. Things are not so simple, okay? But again, you have removed completely some of the things that are disturbing your measurement in rings. So rings are much more complex. I think I have published the results of rings also under this framework, theoretical framework. And the conclusions are, clear. If you have enough volume, if your problem is not of volume, maybe because you have volume problems with the blood you extract, or maybe because you have some uncertainty on the chemical process that is making that your spiral is not being cover at the same ratio everywhere, so you need to concentrate for some of that reasons. If you don't need to concentrate the the sensor itself, then go for interferometer with no doubt at all. Believe me. Okay, these numbers are, okay, we are sensing the 6-digital number in real experiments, and the technique, if you improve it, I think we can get to the 10 to the minus 9 or something like that, which is very, very, very tricky. So, in general, I would say, this is and do it coherent. Why don't use 2 channels to have this beautiful plot and, separate the phase from the amplitude? You can do complex things with this. You can simultaneously, analyze what happens with the phase and with the amplitude. It's all advantages. People in telecom know this for a long period, but in sensors it's not so widely used. I don't know why. They gain too much time.
Yes, it's enough. Just a challenging question, but it's just to make joke of these things. What do you think about detecting a single molecule with this technique?
If you want to
because people working with ring resonators are proud of detecting a single molecule.
If you want to go for single molecule, then of course you have to reduce the size. And of course, this is not going to be useful because for this, the whole spiral must be covered, and you need enough amount of analyte to connect to all the receptors there. So one of the reasons to go to rings, if you want single molecule, a very, very low number of molecules, you have to recirculate the light. The principles are exactly the same. Yeah. Okay, but of course make the light recirculate on the same area or on the same length, so that you can have all these numbers can be done with using just an effective length which is bigger by the resonant Q factor or whatever, Clearly, I mean, I'm not saying the resonant stuff is not good. It's not good for bio stuff when you have enough amount of sample and you don't need to reduce volumes, etc.
Okay, so that's another way to see the things from our face, from our from our wavelength shift area, because we detect with wavelength shift. And this is another way to see things from the point of view of processing, signal processing.
But resonant structures are nice because they concentrate, but at the same time they put a lot of challenges on the instrumentation around, etc. Okay, so that's the reason why if you don't need it, why use it?
Perfect. Yes. Okay, so let's send the speaker again.